Welcome to lecture 2A of the computer architecture and microprocessor system course. Today we are going to be looking at the from transistors to logic gates. How if you go through the hierarchy of the computer systems, we saw that at the bottom was electrons, then followed by devices, and then logic gates. I think it was electrons, then devices, then logic gates. So here we'll be looking at how to use the devices. The devices consist of the transistors. So we're looking at how to use the transistors to design very basic logic gates. We're not going to go into much details, but just how basic devices like the transistors can be used to make the logic gates, like the AND gates, OR gates, XOR gates, and stuff like that. Okay. Now the overall aim of this course is that at the end of the entire at the end of the semester, you should be able to design this single cycle processor. Now, very simple. This is a single cycle processor consists of two kinds of memory. One for storing instructions and one for storing the data. It consists of a register file. It consists of ALU. It consists of the program counter and other components. So we are going to learn how to design each and every component within the system. And after we've been able to design each and every component using low-level languages like the Verilog and using computer-aided design tools like the Vivado, we should be able to combine all the components to be able to design a very simple single-cycle processor and implement that single-cycle processor on the FPGA board. So this is the end goal of this course. Now, you will have, before we get started, we have to know how this kind of code works. This is a very simple, or one of the a very simple C code which just prints out a hello world. Our aim for this course is to learn how a code like this works in the hardware. We already know how the code works in software level, but how does it work on the device it is designed to be implemented on, such as our computers. So we are going to see the underlying hardware within our computer system that makes this a code like this work. Now, a code like this is actually C programming, and then if you have a C language like you initialize your x to be 10, and then you double your x, add it to 15, and then store it within that same x. This is C language. So how does this language translate to machine code? So from C to machine code, because the underlying hardware does not understand the C language you are programming, you are using the program. The C language was actually invented to make sure that the humans are able to program the device itself, and the device does not understand the C language. The device, which are the transistors, at the low level, and the devices are the transistors, and these transistors only understand logic 0 and 1, and on, and then an off, the true, false, 0 volts and 3 volts. Right, this is what the devices within the computer system understand: on, off, 3 volts, 0 volts, true, false. That is all it's understand. It doesn't understand the high level language. So that high level language has to be in a way translated to the machine code, which are made up of only ones and zeros. Right. So first of all, this C code will have to be converted into what is called the assembly language. Now there are a lot there are many forms of assembly languages, but in this course we're going to be learning an assembly language that is relatively new. I think it came in for like it came in probably 12 or 13 years ago. It was designed by some students together with their professor in the UC Berkeley in the United States. So that's they designed it, and then they designed it to be open source. So that's why we are learning it. We can take their 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 ISA. It's called an ISA, an instruction set architecture. We can take it and then we can implement it without any issue. We don't have to request for any license from anybody to use the ISA that they are using or that they design. It's completely open source. So what happens is that the C language, which is the high level language, is converted to the assembly language, and this is the assembly language. This is the assembly language, and then this just means that add I means add immediate in assembly language. Maybe you'll be seeing it in detail very soon. Add I just means add immediate, and then this actually just means that we are adding register R0 to. It means that it just means R5 register R5 is equals to the value inside register R0 plus the number 10. So we add the value inside register R0 will be added to number 10 and then to be stored in R5. This is just add immediate. Now the second one is multiply, which is this one here. We are multiplying the value inside register R5 by 2 and storing it in register R5. And then the last one is we add immediate again. The multiplication is added to the 15. So add immediate again. The register R5 is added to 15 and then stored in R5. So this is just the assembly code. We'll be able to translate from the assembly code to the RIX5 assembly. You'll be able to translate from the higher level C code to the assembly language using a compiler. So that's what a compiler does, translate from high level C code or Java or C++ to our assembly language. Now okay, now from the assembly language, we need an assembler to actually convert the assembly code that is actually designed or that is actually implemented into the machine language itself, which is ones and zeros. And then the machine language, as it can be seen here, it's just made up of ones and zeros. And then this is the RIX5 machine language. If we take each section of the machine language has its use. It's not just random ones and zeros, right? Now for if you take addition, for the addition to be converted into an addition like add I R5 R0 10. Well, an assembly language like this, the machine code is made up of sections. Now the first section is what is called the opcode for add I. So the opcode for add I, and then the next section is what is called will store RS5. So R5 will be stored here. This is known as the destination register. Right now, the next one is known as function. Then the next section stores the value of R0, which is the source register. And then the last section stores the immediate value, which is 10. So it stores the value 10. So this is the immediate store the immediate expectation. So that is so the machine code is not just random, but each section has its use, right? Okay, now as the compilers and then the assemblers have converted the code into machine code, your code will be stored inside what is called the instruction memory, and then the instruction memory will be read one location at a time, and then those instructions will be executed by either the ALU, and then the ALU also reads from the register file, right? So for instance, if we take the add I instruction, right? Once the add I instruction is read, we have a portion of the CPU that will actually decode the instructions to mean that, oh, this is an add I instruction, and then these are the registers we are reading from. Those registers will be sent to the ALU. The ALU will do its computation, and then it will be stored back into the register. So you'll be seeing um, um, this very soon thing in later lectures. Now the IEC. What is an IEC? Okay, now the ISA is what is known as the instruction set architecture. It's just an abstraction between the hardware and the lower level software. Now, um, yeah, there are varieties of the ISAs that are available. We have the MIPS, millions of instructions per second ISA. We have RISC, reduced instruction set computer ISA. We have the CISC, complex instruction set architecture, complex instruction set computers, and then we have but now what we are going to study will be RISC 5, reduced instruction set 5 computers. So that's what we are going to be studying. So the ISA is an abstraction between the software and then the hardware. So you take your software, it will be translated into an ISA, and then your hardware will be able to execute that particular ISA, right? Now, when you take a basic computing system, basically each and every computing system consists of three main components, which is computation, communication, and storage of memory. And the storage is made up of the memory system and then the storage system. Now, when you talk about, there are a little differences between the memory and then the storage. Practically same operations, but based on where they are located. The memory is actually always located on the chip, right? So that's why we call on chip memory, and then this memory is just used to actually store programs on the programs that do not actually change. So programs that are not, they used to store programs for this that will be executed by the CPU. The storage exists outside the chip. It's off chip memory. This is usually so this is usually larger than the on chip memory. So this storage will store some kind of computation data that you want to execute, right? So there's clear difference between the memory and the storage. Now the computing elements will have to communicate with the memory element, right? We have the computing element, and then computing element, and then you have the memory. So the computing element communicates with the memory element through an interface known as the communication unit. So the communication unit here will enable communication between the computing element and memory. Okay, when it comes to the computing units, traditionally it was mainly made up of the CPU. So you had the CPU, then you have the communication um, link, and then we have the memory. But the CPUs are slower now. Now, for instance, to do matrix multiplication, the CPU will take a very very long time to complete just one matrix multiplication. So now we have specialized hardware that supports the CPU to be able to execute mathematical complex mathematical functions that involve parallel involves parallel kind of communication, right? So the computing we made up of CPUs, we made up of GPUs, we made up of again what we are studying, the FPGAs. FPGAs we made up of specialized ASICs and a lot of different components that will come together to support or to support basically the CPU, because works from the CPU, if it involves parallel processing, will be delegated to the GPU, the FPGAs or the ASICs, right? Now the processor basically executes instructions that are stored in its instruction memory, right? So the memory will hold some kind of instructions that which is usually the machine code, and then we have and um, and we have different types of kind of different types of processing or the computer system based on how the instructions and then the data is stored. We have one which is known as the von Neumann architecture. Von Neumann architecture, and then we have another which is known as the Harvard. Von architecture, with the von Neumann architecture, the instructions and then the data are stored in the same memory location. Like so, you have instruction and data stored in the same memory. You have some kind of partitioning in the memory that will indicate that the instructions start from probably from this is instruction and then this is data. So probably from this point to the from the beginning of the memory to the middle will be for instruction, and then from the middle to here will be the data. Right now, this has this uh, down for this has its merits and then demerits, as you will be seeing very soon. We have the Harvard architecture also, which which stores instruction in one memory and then data in another memory, a separate memory, right? So we have instructions and data are stored in completely different memories. Now let's look at architectures like this. Now for just one memory with the von Neumann architecture, it means that we cannot read um, instructions and data at the same time, right? So it means that the von Neumann architecture is actually slower. You have to read instruction, and then you have to actually um, also read data at a completely different time. So what you can read and read instruction and then data at the same time. Then you can write to the data memory when we're reading the instruction memory. So it's kind of slower with the Harvard architecture because they are two completely separate memories. Now you can actually read and write to those two different memories at the same time. So it actually makes it a little bit faster than the volume architecture. But the downside to the Harvard architecture is that it wastes a lot of memory. For instance, if the instruction memory is not filled up and then the data memory is not filled up, you've actually wasted some kind of memory. Meanwhile, for the Java architecture, there some parts, because we have been able to fill up an entire memory with instructions and data. This is much more efficient than using the Java architecture. Right, and there is usually a bus that connects the processor to the memory. So you have to take notes, and then this bus is also quite important, as we'll be seeing in later lectures. Now, what we're going to cover in this course is the ISA, which is the instruction set architecture, the microarchitecture, and then the logic gates. We are not going above the ISA, and then we are not going below the logic. So where does it all begin from? Digital systems or modern computer systems started from the design of a single transistor. I think the transistor was designed in 1945 by some 3 scientists. So they discovered, or they designed this transistor in 1975, in 1947 at the AT&T Bell's lab. And then the transistor just works as a switch, just your switch. You turn it on, and then the current flows through. You turn it off, the current is cut off. So that's how it works. It's just binary. So it means that the output is actually on or off. So just binary, 1 or 0. Right. Now computers actually built using very, very, very large numbers of transistors. Right. If you look at the Intel 4004 CPU which was designed in 1971, it had about 2300 MOS transistors. The MOS just means metal oxide semiconductor transistors. Now, fast forward, if you take the Apple M2 Max, which appeared in, I think, 2022, is made up of 67 billion MOS transistors. So from 1971, which was 2,300 transistors, to 67 billion transistors. So you can see that the scaling has really scaled. So the number of transistors on the computer system nowadays is in the billions, right? Now, the MOS transistor is designed by combining a conductor or conductors, which is the metal, and then an insulator, which is the oxide, and then a semiconductor. So that's why we call it the metal oxide semiconductor. And then for the metal oxide semiconductor transistor, we have the gate. You apply a voltage to the gate to actually turn on or turn off the MOS transistor. And then we have the source, where you connect your voltage source to, and then we have the drain, where the current will flow from the source to the drain. Now we can combine this MOS transistor to design different logic gates that we will be using to implement larger digital systems, right? And then the MOS transistor, or the transistors, are actually the lowest abstraction, which are the devices. You will just look at briefly what it is about, and then see how you'll be able to use them to design logic gates, but we won't go too much into details. Right? There are 2 types of MOS transistors. We have the N-type and then the P-type. So the N-type MOS transistor, and then the P-type MOS transistor. What all this means is that for the N-type semiconductor, for the N-type MOS, this is the N-type. Then we have the P-type with a dot or a circle here. The N-type just means that this is the gate of both gate here. The N-type means that L1 turns this device on. So L1 will close the device if it is actually the L1 will close the circuit and make current flow from one end to another. A 0 turns this device off. Once you apply a 0 volts to the gauge, the device is turned off. For the NMOS, a 1 turns it off. Is the opposite of the PMOS, is the opposite of the NMOS. So for the PMOS, a 1 turns it off, right? So once you apply a 1 here, or the logic 1 here, or a 3 volts here, the device will be turned off, or the device will become an open circuit and current cannot flow through. But once you apply a 0 logic or a 0 volts, the device is turned on, and then current can flow through it. So they are just opposite. So if you want to know why a 1 turns it on, you have to go and study semiconductors, which is not the focus of this course, right? So the MOS actually behave just like a switch, as I said. So if you have your wall switch here, once the lamp will actually go when electrons flow through the system, and then once there's no cut, right? So in order for electrons to flow, there must be a closed kind of a circuit from the power supply to the lamp, and then the lamp is turned on and off by simply manipulating the wall switch to make or break in the closed circuit, right? So if you close it, it turns on. If you open it, it turns off. So this is how normally the switch works, and then this is how the NMOS and then the PMOS works. So instead of reusing the switch, you can, in place of the switch, use an NMOS or a PMOS. NMOS consists of the source and then the drain, and then that is the schematic of the NMOS, right? Now, as I said, you supply a high voltage. Once you supply a high voltage, or you supply the logic 1 to the gate, it will close, and then it will actually allow current to pass through it. And then if you supply, or you don't supply any voltage to the gate, or 0 volts or 0 logic, right, the gate is actually, or the device is actually serve as an open circuit, and then current cannot actually flow through it. So once you connect your MOS transistor to the switch here, and then you apply 3 volts, the bulb will actually light up, and then the PMOS is just the opposite of the NMOS. One, you have to apply a 0 volts for it to turn on. Right. Now we have seen how the MOS transistors work. We have an NMOS and then the PMOS. But how do we build logic structures out of this NMOS? Right. That is what we are going to be looking at next. And for we to build logic gates, I mean, modern computers used to be made up of only NMOSs. Right? We used only NMOS to actually make. Previously, we used only NMOS to make our computing systems, because the NMOS, the flow of electrons were easier to handle than the flow of holes. If you study more, you will know that NMOS is based on the flow of electrons, while the PMOS is based on the flow of holes. The flow of holes was difficult to handle back then, so modern computers or previous computers always use the NMOS. But recently, the holes have been able, the flow of holes have been able to be, due to the advancements of technology, the flow of holes have also been enhanced, and then is being made use of. So now modern computers are implemented using both the NMOS and the PMOS, and then once we are able to combine the NMOS and the PMOS, this is what we call the CMOS, right? So the CMOS is what modern computer systems actually use. We have an NMOS combined with a PMOS. This is used to design our logic gates, and a MOS plus a PMOS will give us a CMOS. Right, and then this is one of the simplest logic structure that exists in modern computer. Right, we have the simplest CMOS structure. We have a 3 volts here. We have our PMOS. We have our NMOS. Yeah. We have our input, and then we have our output. Right. So this is a simple combination to form a logic gate, and to find out how this logic gate works, we have to actually draw the truth table of this logic gate. We have inputs. Let's say the input is A, and then our output is Y. So we have to draw our truth table, and to draw a truth table, we have our input A, and then our output Y. This is just one bit, so we have a 0 and 1. So what we have to do is that we have to pass the inputs 0 and 1 through the circuit and see what the output produces. Now, mind you, in the PMOS turns on, or the PMOS will allow current to flow through it if a 0 is applied, and NMOS will allow current to pass through it if L1 is applied, right? So once we apply a 0 here, a logic 0 here, this point will be a 0, and then this point will be a 0, right? And then we say that a 0 turns on the PMOS, and then a 0 turns off the NMOS. So this NMOS is off, and then this PMOS is on. So it will allow the voltage that is here, will allow the current to flow through the circuit to the output. So when we have logic 0 applied to this, the input of this gate, the output will be a 3 volts, which is 1. Right, simple as that. Now, yet again, you have to pass 1 through the circuit and see the output. Now, if we apply a 1 to the input of this circuit, a 1 will appear here, as 1 will appear here. For the NMOS, a 1 turns it on. For the PMOS, a 1 turns it off. So this PMOS is off. Actually, this is connected to the ground. So this NMOS will turn on this circuit, and then the voltage that is on the Y will flow to the ground. And this, once you connect anything to the ground, the voltage flows through it. Voltage will flow to the ground, and then the ground is at a logic 0, so the output will be 0. Right. So with this kind of circuit, if the input is a 0, the output is a 1. If the input is a 1, the output is a 0. It simply means that the output is an inverse of the input. So Y is equals to the inverse of the output. So this is just what this gate is what we call an inverter. Right. That is how we use the PMOS and then the NMOS to construct an inverter. And then the symbol for inverter, you already know the symbol for the inverter is simply this with a dot here. A, Y. This is the transistor level design, and then this is the gate level design of our simple transistor. Right. Now, Okay, now let's look at more complex design. This is a very simple design. This is the basic logic gate, which is the inverter, the NOT gate. Right now, so now let's look at a more complex system like this. For this kind of system, we have the PMOSes which are in parallel here, and then we have the NMOS which are in series here. The NMOSes are connected to a 0 volt. The PMOS is connected to a 3 volts. We have output, and then we have two inputs in A and in B. So what kind of gate is this? Right. So we have to pass through or pass some logic or pass some ones and zeros through the circuit to be able to figure out what this circuit is. But it's simply a CMOS NAND gate. But how does it work, or what is the truth table? And what happens is that the PMOS is P1 and P2 are in parallel. So it means that if any of them is on, the circuit is on. Right. Now the NMOS here are in series. So if any of them is off, the entire downside is off, right? So that is how the CMOS NAND gate work. Now here, first of all, let's pass a 0 0 to our circuit. Once we pass a 0 here, a 0 here, these two transistors here will be turned on, right? And once we pass a 0 to N1 and N2, these are turned off. So once P1 and P2 are turned on, the voltage here at the output will be 3 volts. So it will be a logic 1, right? Next, if we pass A to be 0 here and N to be 1, A to be 0 turns on PMOS 1 and turns off PMOS 2, right? And then A to be 0 turns off NMOS NMOS 1 and B to be 1 turns on NMOS 2. But then once one of this one is off, this part of the circuit is cut off, and because A is 0 and P1 is on, the voltage will actually the current will be able to flow through from the treble, from the top to the output. So it is also a 1. The same goes for 1 1 0, but when it comes to 1 1, a 1 1 will turn off P1 and P2 while it turns on N1 and N2. So once N1 and N2 are off, the voltage will be grounded, and then the output we say is 0. That is the truth table of the CMOS NAND gate, right? Now, when we have a NAND gate, you'll be able to see how the CMOS NAND gate operates. Now, we want to design the CMOS AND gate. How do we design a CMOS AND gate? But we've already seen the NAND gate. The NAND gate is just the inverse of the CMOS AND gate. So all we can do is we just connect an inverter. This inverter to the output of the CMOS NAND gate we just looked at, and then we will have a CMOS NAND gate. So we just connect an inverter here to the output of the CMOS NAND gate, and then we will have the CMOS AND gate, right? So this is the symbols, the logic gates as you already know for an inverter or a NOT gate, the truth table, and then this is the logic or the device level, the transistors configuration level, and then this is the NAND gate, the truth table, and then the transistors, and then this is the AND gate, the truth table, and then the transistors. So here we can see that designing circuits with NAND gate and then AND gate. Once you have a design that you are using only AND gates to design or only NAND gate to design, the AND gate use more transistors than the NAND gate. So as a designer, you have to once you're designing and you're designing a system that requires very less number of gates, then you need to look at a combinations of the NAND gate to use for your design. That will actually make your system smaller, right? The number of transistors in a semiconductor increases every few years due to the advancement in the technology. Now, the technology is that the transistors were actually if we take a transistor, this is the NMOS, right? We have what is called here as the channel, right? So once a transistor is designed based on a technology, the channel width of the channel is very important. And previously, for the first design, the channel were so big to the point that you couldn't on a single chip you couldn't fit a number of these transistors there. But as technology has advanced to a point that we are being able to shrink this transistor to a point that we make this channel closer. That is a way to shrink the transistors, by making the channel closer. So by doing this, each and every year or each and every couple of years, the transistors are becoming smaller and smaller, and then we are being able to fit on the same single entire die or single die. You'll be able to fit a lot of transistors within the same die that were used. Let's say the dies that were used 10 years ago. Within this period, you'll be able to fit more transistors on it. And then Gordon Moore was able to predict, I think in 1965, that the number of transistors in a computer system is going to double every 18 to 24 months. So every 18 to 24 months, the number of transistors there will double. And then that has been true for a number of years. From 1970, if you look at the processors that have been produced, and then to around 2005, around 2005, 2006, if you look at that trajectory, the number of transistors have been increasing every 2 years. But now there are a couple of issues we have now because of the channel width I just talked about. One of the issues with the shrinking of the transistors is that the channel width, once you bring it too close together, there will be kind of leakage voltages, right? So that has actually made the shrinking of the transistors to actually slow down. So transistors are no longer being shrunk like they were before, and then that is one reason. And then also, once you have a lot of transistors on a single chip, you have to take care of heat. It means that the transistors produce a lot of heat that would need to be taken care of, and then the semiconductor industry is struggling to actually remove heat from the chips. So the scaling, the number of transistors have been doubled, have slowed down within this decade. So the Moore's law have actually slowed down within this decade, but it has been true from 1970 till around 2005. So it's really done well in predicting that the number of transistors will double every 2 years. But for this decade, because of a number of issues with the design itself, the Moore's law have actually slowed down. And this is the end of this lecture. Thank you.